Alright, so what I'm going to go through here is I'm going to give you a little introduction to what differentiation is. Basically what we're going to talk about is what a derivative is and what the power rule is and the chain rule is. The first thing that I'm concerned about is that some of you are going to read through this and see that the notes, it's not part of the notes, and you're just going to skip ahead. And I can't stress that these first beginning part of this video is really important as far as understanding conceptually what's going on. Mathematically, there's some rules to follow, and it's not that complicated once you learn the rules. But the problem is people learn the rules and they forget what it is they're actually doing, and so then when problems come up like word problems, then they don't really understand what's going on because all they know how to do is some rules. Trust me, it's to your advantage to try to follow along in this beginning part. I don't expect any of you guys to be an expert at this when you get back on Thursday. Relax and take in what you can. I promise that it's going to make more sense when we do more practice. But try really hard to get what you can from this. Alright, so let's talk about this. How do we measure speed? So Robbie gets in his car and he drives to his uncle's house 5 miles away. And he arrives after 15 minutes. How fast was he going? Typically what we would do is we'd probably figure out his miles per hour. And that's basically just distance divided by time. If I were to graph how far he went and how long it took, then it might look something like this. And if I wanted to find out how fast the car was going, then I might use the slope formula to figure out the slope of this line. If you take a look at these points here, if I just were to go ahead and use these points and find the slope, I would be doing 250 minus 50 over 5 minus 1, or 200 over 4, or 50 miles per hour. And if you take a look at this, if we went 250 miles in 5 hours, well, that would be 50 miles per hour. What's different is that typically, if you're driving 5 hours, you're not driving the same speed the whole time. What happens is that we'll typically say, oh, you went this far and this is how long it took. So on the average, this was what your speed was. In this scenario, we've got graphed here. This person drove for 5 hours at exactly 50 miles an hour the whole time. The slope is how we measured the speed, and that's not a big change or a big surprise, I think, because the slope of a line is the constant rate of change. How fast is the car going at this point? Well, we've already said that based on the scenario we've described, he's going to be going the same speed. He's going to be going 50 miles an hour. If this was the situation, they're clearly different speeds. At this point, how fast is this guy going? Well, if we use the same notion and figure out the slope, well, then it would be 100 minus 0 over 2 minus 0. He'd be going 50 miles an hour. Now, what about here? How fast is he going now? Well, you notice his distance is not increasing, but time is increasing. If I go ahead and plot 2 points, 3 100 and 2 100, you'll find out when I do the slope formula that I end up going 0 over 2, or he's going 0 miles an hour. Here, you see we've picked up speed again, and if I want to know how fast I'm going, I could just plot these 2 points and then use the slope formula for them, and I will be going about 16.7 miles an hour. If I'm still on the line, even if I'm a little further along, based on this scenario, I'm still going the same exact speed. And then here, my distance is not increasing, but time is increasing, so I'm going 0 miles per hour. And then you'll notice here, if I want to find the speed, I plot these points, 10, 300, and 8, 150, and I get 75 miles an hour. Now there's a couple different reasons for going through this. I want you to notice, number one, that the steeper the slope, the faster, the higher the rate of change is. And you also notice that when the line is horizontal, there is no rate of change, or the slope is 0. In this situation, we've got a parabola, and basically, if you want, we've launched some kind of rocket, and 4 seconds later, it hits the ground. So the time along the bottom, here's the seconds, 1, 2, 3, 4 seconds, and then the height is along here. This is how high it goes. At 1 second it was 48 feet, at 2 seconds it was 64 feet, at 3 seconds it was back down to 48 feet, and then at 4 seconds it was at 0. How fast was it going at 1 second? At this point in time, at 1 second, how fast is this rocket going? What about how fast is it going at 2 seconds? And see, this is harder to figure out because it's not a straight line. The speed is constantly changing in this situation. Down here lower, it's increasing its speed, it's accelerating, it's getting its maximum velocity, but then it starts to slow down here. It gets slower, slower, slower. In fact, at the vertex, there's a millisecond where its speed, it's basically stopped. It's not going anything at all. It's not going any higher, and time is passing. And then what happens is it starts to go down. And again, it's going to slowly increase its speed and then come back down. The problem is figuring out the speed at any one particular point is more difficult on a curve than on the graphs we were looking at before because they were all straight lines. So finding the specific rate of change of a curve at a specific point in time, or an x value, is one of the things that we use calculus for. If I want to approximate the rate of change of the rocket at this specific moment in time, after 1 second, then what I would use is I would typically draw a tangent line. And then the tangent line, once I found the slope of it, then that would be the rate of change at that exact moment. And see, I can take these points, 148 and what's this, about maybe 0.12. And if I figure out the slope, it's going to be at that point in time, at that right then, 1 second, it's going to be going about 36 miles an hour. If I were to check a little bit earlier, it'd be a different speed. And if I were to check a little bit later, it'd be a different speed again. So it's going to go about 36 feet per second. At this particular time, if I use a tangent line, you'll see that a tangent line at this point is going to be horizontal. And so the slope of a horizontal line is 0. At that particular point, it's going to be going 0 feet per second. And then if I were to go on this side, what would the rate of change look like over here? Well, you'll notice how it's negative. And so that's a negative slope. Note that the rate of change is positive as it increases a maximum point. It's 0 at the maximum point, and then it's negative after the maximum point. This is going to come up later. So it's possible to find rates of change for a curve at different values by using tangent lines. I hope you can appreciate that if different people are drawing different tangent lines, it would be very unlikely that people would draw the same tangent lines and that they would be perfect. And so it's not a very precise method to use to find a speed at a particular point. So what we're going to do is we're going to use derivatives to find these speeds at these particular points of a curve. Now the thing is, we're going to use what we said was the power rule, and we're going to be using what's called a chain rule to find these derivatives. And I know you don't know what a derivative is just yet. Don't worry, we're going to get to that. The fact that we're going to be using these power rule and this chain rule, and we're going to be manipulating the exponents. It's important that we are going to get the exponents of our variables out of the denominator of any fractions. I want to just kind of review it real quick before we get to the rules. So for this first one here, you'll notice we have got 3 over x squared. Now, if I'm going to use my power rule, I want the x to be in the numerator. So what I'm going to do is, in order to make that happen, I'm going to raise it up to the numerator, but then it's going to be x to the negative second, not x squared. If you take a look at this one, number 2, I hope you'll realize that the square root of x, the same thing is x to the 1/2 power. And again, when we run into things that are square rooted, we're probably going to change them to the 1/2 power because, like I said, it works really well with this power rule that we're going to be using. In number 3, you'll notice we've got 3x times x, or the square root of x. And so that really is 3x times x to the 1/2, if I rewrite it. And then you'll notice when I multiply two bases that are the same, I add the exponents. So that's going to be 3x to the 1 plus 1/2, or 3x to the 3/2 power. And it's even possible that we would write it as 3x to the 1.5 power to make it even easier yet. If you take a look at number 4, you'll notice we've got x over 2 square root of x. Now, I'm not worried about this 2. It can stay in the denominator all day long. I am worried about this x. Now, the thing is, you're like, well, it's not a power. Well, that's true, but when we rewrite it like this, it is going to be a power. And so now I need to get this x with this 1/2 up here in the numerator. Now, whatever is up there already, it's going to get multiplied times it. So when I move this up, it's going to be x times x, not to the 1/2, but to the negative 1/2, because it's moved from the denominator to the numerator. And notice how the 2 stays down in the denominator, because I don't care where it's at. Now, when I multiply these together, it's going to be the same deal. It's going to be the bases are the same, so I'm adding the exponents of 1 and negative 1/2. And what I'm going to get is x to the 1/2 all over 2. Let that sink in. Now, let's take a look at number 5. Here, hopefully you're familiar with this. All right, the 5 I'm okay with. I can rewrite this. Now, this is not a square root. It's a cube root. And so what this is going to be is the same as is 5 times x to the 1/3 times x to the 1/3. This is going to be 5 times x to the 2/3 power. And maybe you remember in Math 2 or where you had the rule where this is the power, and then whatever the root is, that was the bottom part of the fraction. Like I said, if this had been a 2, the square root, then it would be x to the 1/2 power. And if this was x squared, it would be x squared to the 1/2 power, or x to the 2 over 2, which would be x. Anyway, let's look at this one. You'll notice how we've got this group down here. First we're going to change the square root to the 1/2 power, and then our job is to take this guy and move it to the numerator, and the whole thing is going to move up there, and it's going to be multiplied times 2. So it's going to end up looking like this: 2 times 3x plus 2, and it'll be to the negative 1/2 power. Now, mind you, only this 3x plus 2 is to the negative 1/2 power, because that's the part we moved. 2 is still to the first power. You don't got to write that. So let's take a look at here. 4 over x minus 2 to the 3rd. In this one, what we got is a cubed binomial down here at the denominator, and I want to move it up. So it's going to be 4 times x to minus 2 to the negative 3rd power. All right. Now let's talk about differentiation. It's basically the process of finding the slope or gradient of a tangent line to a curve at a specific point. And that point is designated by its x value. And you'll see why in a minute. A derivative is actually a function, and it's used to find the slope of another function at a given x value. So there's some different notation that we use. If y is a function of x, then we'll say that the derivative of y with respect of x, and you'll see this written. And basically this means we're finding the derivative. And you also sometimes, when the function is written in function notation, then you'll see us use this where we just do this apostrophe, we call it f prime of x. And it's also a derivative. And there's no big deal difference. We'll use this notation when it's a y equals equation. We'll use this notation when it's an f of x equal equation. And there's even this notation down here, d over dx to the x squared. And I don't see that very much. Most of the time it's going to be these guys here. So, basic differentiation. And the rules are pretty simple. If I wanted to find the derivative, a constant, well, let's think about that for a second. A constant, y equals 3. So all this means is I'm going to find the derivative of a number, c. Well, in this case, that number is 3. So if I want to find the derivative of y equals 3, well, if we take a look at a graph, that's a horizontal line. Now imagine a tangent line at any point on here. A tangent line, that means it's going to touch it. Well, it's almost impossible because it touches it at one point. But anyway, a tangent line is going to have a slope of 0. And so the slope of any constant is going to be 0. If you're asked to find the derivative of a constant, the answer is always 0. And so let's look at that. What's the derivative of f of x equals 6? It's 0. What's the derivative of f of x equals 37? It's 0. What's the derivative of f of x equals negative 1? It's 0. It's just that easy. So if you're finding the derivative of a constant, it's always going to be 0. Now, if I'm going to, the power rule, and basically if I'm finding the derivative of anything with a power, all I'm going to do is take that power and multiply it times the front, and then I'm going to take whatever the power was and subtract 1. Now I know it's a little complicated, but it's not nearly as bad as it looks. So here, you see this 3? It's going to come down in front, and then it's going to look like this. And then I'm going to take that 3 and I'm going to take away 1 from it, so it's going to end up being 3x squared. Try this one. If I want to find the derivative of this, I'm going to bring the 5 down in front, and then what I'm going to do is I'm going to take away 1 from the exponent, and that's going to leave me with 5x to the 4th. So try this one. I'm going to take the 9, bring it in the front, and then I'm going to make the 9 minus 1, and that's going to give me 9x to the 8th. The derivative of x to the 3rd is 3x squared. The derivative of x to the 5th is 5x to the 4th. The derivative of x to the 9th is 9x to the 8th. Alright, so try this. Find the derivative of f of x is equal to x to the 4th. We're just going to use the power rule. So we're going to bring the 4 down in front, and then we're going to take 1 away from the 4, and I'm going to end up with the derivative being 4x to the 3rd. Now, that might be said that that's the derivative. The derivative of this function is x to the 4th is 4x to the 3rd. The derivative of a function is a function that I can use to find the slope of a tangent line. So let's take a look at that. But first, let's change the notation. What if I make it look like this? Y equals x to the 4th. The directions may say find this, which means the derivative of y in terms of x. Now, all I'm going to do is the exact same thing. You notice how the fact that it used to say f of x and now it says y equals? The problem is exactly the same. I'm going to bring the 4 down, I'm going to take 1 away from the 4, and that's my derivative. Both of these mean the same thing. Anyway, the words we would use be the derivative of a function with y with respect to x is 4x third. So, if I've got this derivative, what can I do with it? So I want to take a look at a graph of x to the 4th. This is x to the 4th. Now mind you, that's what we started with. Now say I want to find the slope at a particular point. And the point I'm going to pick is going to be -1. Now if you take -1 and plug it in there, -1 to the 4th power is going to be 1, so you can see where this point is. But you'll notice that when we have a derivative, it usually is in terms of x, and that's why we're always interested in having the x value, because that's what we're going to plug into it. So anyway, here's my derivative, 4x to the 3rd. Now if I want to know the slope of this function at this point, all I've got to do is take -1 and plug it in for this x. So that's going to be -1 to the 3rd power, which is going to be -1, and then it's going to be times 4, and that's going to give me a slope of -4. So if I've got a slope of -4 for a tangent line, and I happen to know that this point is at x equals -1, could I find the equation of the tangent line? Well, sure I can, because if I've got a slope and a point, I can find an equation of a line, and that's going to be something you're going to have to do. You're going to have to be able to find the slope of a curve at a particular point, and then you're going to have to find the equation of the tangent line. So, differentiation, it's a process of finding the slope of a tangent to a curve. When you find the derivative of our slope formula, sometimes it's called, you are differentiating. The derivative is a function we use to find the gradient or slope of a curve at any point on the curve. So what if there's a power in front of the x? Oh, I'm sorry, what if there's a number in front of the x? How do we find the derivative then? Well, it's pretty much the same thing. I'm going to take the n, I'm going to bring it down in front and multiply it times whatever number is there, and I'm going to subtract 1. So it makes a little bit more sense if you see it with numbers. So notice that there's a number in front of my x. If I want to find the derivative of this, I'm just going to bring the 5 in front, so it's going to become 5 times 7, or 7 times 5. And then I'm going to take 5 and subtract 1 from it. So my derivative is going to be 35x to the 4th.